This is part 5 in our series of lectures on proofs of theorems on finite sets. And in this theorem we're going to talk about the cardinality of the set theoretic difference of two finite sets. And here's the main theorem we're going to consider. If A is a finite set and C is any subset of A, then the set theoretic difference A minus C is finite, and the cardinality of A minus C is equal to the cardinality of A minus the cardinality of C. So let's look at the proof of this theorem. The main tool that we use is going to involve that theorem we considered a few lectures ago, which says that the disjoint union of finite sets has a cardinality which is the sum of the cardinalities that make up the union. So how could we use that here? The idea is to make use of this subset C in order to write A as a certain disjoint union. So let's make a Venn diagram to illustrate what's going on here. If we let this big circle denote the set A, and C is going to be some subset of that, so C is, say, over here, then that suggests that we can use C to partition A into two pieces. This piece here is A minus C, and therefore A is A minus C union C. So that's a disjoint union. And so what we can do is we can then calculate the cardinality of A by writing it as the sum of the cardinality of A minus C plus the cardinality of C. So we're using the theorem from the previous lecture. If we do that, then if we just simply subtract the cardinality of C from both sides, we get exactly the result that we're looking for. So that's the idea of the proof. So here are the details. First of all, since A minus C and C are both subsets of A, and A is assumed to be finite, it follows from the previous lecture video that A minus C and C are both finite. We also have this way of writing A as a disjoint union, and by the theorem concerning the union of two disjoint finite sets, we know that the cardinality of A, of course, is equal to the cardinality of this, but the cardinality of this, if we apply that theorem, that's the sum of the two cardinalities. Now, of course, these are numbers, right? This is a number, this is a number, this is a number, and if we just simply subtract this number from both sides, we get this. And that completes the proof of the theorem. So I claim a corollary of this result is that any finite set does not have the same cardinality as any of its proper subsets. So do you see how we could prove that using the result that we've just considered? See if you can figure out how to make use of the result we've just proved in order to show this proof of the corollary. Well, so we give ourselves a finite set, we give ourselves a proper subset of it. Of course, we're going to, so that implies, of course, that A is non-empty. So by the theorem, we know that we have this. Now, what does the fact that C is a proper subset of A tell us about this left-hand side? Well, the fact that C is a proper subset of A tells you that the set A minus C is non-empty. And the fact that it's non-empty tells us that it must have a positive cardinality, and therefore this must be a positive number, and therefore this is a positive number, and so that proves that the cardinality of C is strictly smaller than the cardinality of A, and therefore C and A cannot have the same cardinalities. That completes the proof. Compare this to the analogous situation for infinite sets. It's very possible for proper subsets of infinite sets to have exactly the same cardinality as that infinite set. For example, the set of even natural numbers is a proper subset of the set of natural numbers, yet they have exactly the same cardinalities. So we've shown that such a thing cannot happen with finite sets.